10 Sources of Climate Change, Climate Science Series. There are a great many misconceptions about climate these days. Some of them are based on half-truths, while others are based on outright lies or clever misdirection. The following are the top 10 sources which drive climate change. Number 10. Insolation. That's right, the sun. Without it, our world would remain in frozen darkness and climate change would become stopped entirely. Thankfully, our sunlight remains amazingly constant from day to day. However, the light of the sun changes over time, increasing by 10% every billion years. A billion years after the sun first ignited, it shone with about 1.1 times its original brightness. Today, it shines at about 1.54 times the original, and after 10 billion years in the main sequence, right before evolving into a subgiant star, our sun will shine with about 2.59 times its original brightness. Of course, this change is extremely slow. Since animal life first appeared on Earth about 500 million years ago, the sun has brightened only about 4.88%. Number 9. Shapes and positions of the continents and paths of ocean currents. The shapes and positions of the continents and the flow of the ocean currents affect climate greatly, but continent positions change very slowly, coming together on a scale of approximately 200 to 400 million years, and then splitting apart again on a similar timescale. There have been several supercontinents in the history of Earth. Not only do the sizes and shapes of the continents affect the climate, but the relative positions of the landmasses do as well. For instance, a huge continent like Pangaea suffered great heat in huge deserts because water could not easily reach the interior. From about 43 to 34 million years ago, Antarctica drifted from being completely north of the 70 degrees south latitude line to touching the 85 degrees south latitude line. At the same time, the space between Australia and Antarctica opened up, allowing a circumpolar circulation to form, cutting off warmer water from reaching the southernmost continent. About 34 million years ago, about the start of the Oligocene epoch, temperatures plummeted dramatically. While still far warmer than at any time during our current ice age, it was enough to cause Antarctica to become heavily glaciated. Number 8. Galactic orbit. During a talk given by Israeli astrophysicist Dr. Nir Shaviv, the scientist revealed that some of Earth's ice ages fit a pattern of passage through the disk of the Milky Way galaxy. A period of about 147 million years between ice ages is roughly half of the orbital period of the solar system around the center of the Milky Way galaxy.
And we can see how ions increase the condensation of small aerosols, an experiment which was then repeated at CERN. And we can see also two different mechanisms which increase the survivability of the small aerosols to become large aerosols. One was already published, the other one is going to be published. The only thing missing is to take these mechanisms, plug them into a global aerosol model, and then see what the global effect is. And this is research which is on its ongoing research, which should be published this year. On long time scales, and with this I'll almost end, there are huge variations in the cosmic ray flux due to the fact that we pass through spiral arms of the galaxy. It turns out you can use iron meteorites to see how the cosmic ray flux has changed. And every so often, every about 145 million years, we pass through a region where there's much more star formation and acceleration of cosmic rays around us. And you can, using the geochemical analysis in fossils, you see here at the bottom graph of the top panel, you see a temperature reconstruction on one hand, and you can compare that to the cosmic ray flux reconstruction based on iron meteorites, and you see that cosmic rays affected the climate over the past billion years.
Currently, the sun's position is between 0 and 20 parsecs above the galactic plane, according to a paper by John and Safi Bakhal. Passing through cosmic ray zones in the galactic disk is only one way our climate could be affected. As more cosmic rays pass through our atmosphere, more cloud droplets are formed, like the droplets in a hydrogen bubble chamber. Another source of climate change from our galactic orbit is the random possibility of passing through a galactic cloud with all the problems that poses. Number 7. Cosmic impacts. The giant meteor which struck the Earth 65 million years ago created a temporary winter from the dust it sent into the atmosphere. That last big one killed all of the non-avian dinosaurs. Thankfully, such massive impacts don't happen very often. There is no way to know whether or not we will have another one in our future. Number 6. Supernovae. It has been several centuries since humanity has seen a supernova in our own galaxy, but the Milky Way is a big place, and there is plenty of dark dust obscuring the view. Most such supernovae would have relatively little effect on Earth's climate. Like any light, the farther we are from its source, the weaker the signal. In this case, we're concerned about the cosmic ray flux. Any supernova within about 3,000 light years could do measurable damage to the biosphere, but that amount of particle radiation could also affect our climate as well. Based on the frequency of supernovae in nearby galaxies, scientists estimate that there are on average between 2 and 12 supernovae per century in our own home galaxy. That's an educated guess, and a rough one at that. Using their most extreme rate estimate of 12, we can calculate the average length of time between dangerous supernovae within reach of Earth. With a diameter of about 200,000 light years and a thickness of about 1,000 light years, our galaxy contains roughly 4,400 potential danger zones. With 12 supernovae occurring every century, the possibility that a supernova will explode in our own zone of danger requires about 300 centuries, or 37,000 years on average. If 2 supernovae per century is more accurate, then we're looking at 222,000 years on average between dangerous supernovae. According to the work of Heinrich Svensmark, Nir Shaviv, and others, a heavier than usual dose of cosmic rays bombarding our atmosphere will provoke far greater rates of cloud formation, increasing Earth albedo and lowering the planet's temperature. Besides the adverse radiation bombarding our bodies, all of life, especially that on land, could suffer another bout of deeper Ice Age cold. Number 5. Milankovitch cycle, orbital eccentricity. On a similar timescale, changes in the eccentricity of Earth's orbit modifies our climate on a cycle of roughly 100,000 years. Eccentricity involves the shape of our orbit. An orbit with an eccentricity of 0 is a perfect circle. The largest eccentricity is 1.0, which is a straight line. Most orbits are some degree of ellipse. The greater the eccentricity, the more extended the ellipse. Because of the gravitational pull of the Sun and the other planets, Earth's orbital eccentricity varies between virtually circular, an eccentricity of 0.000055, and slightly elliptical, an eccentricity of 0.0679. The more elliptical an orbit becomes, the greater the difference between the Earth's closest approach to the Sun, perihelion, and farthest distance, aphelion. Naturally, this creates changes in climate because when Earth is closer to the Sun, everything gets warmer, and when it's farther from the Sun, everything gets colder. Number 4. Volcanic eruptions. Volcanic eruptions can cloud the sky with dust particles that block sunlight, thus greatly cooling our world. Volcanoes with a volcanic explosivity index, or VEI, of 6 occur once every 50 years or so. This is similar to the Mount Pinatubo eruption of 1991 or the Krakatoa eruption of 1883, both of which cool the planet measurably. A VEI of 7 occurs about once every 500 years. This is similar to the Mount Tambora eruption in 1815, which gave us a year without a summer in 1816. That was frightening enough to prompt Mary Shelley to write her best-known work, Frankenstein. It's also similar to the Thera Island eruption, which greatly damaged the Minoan civilization about 1620 BC. Number 3. Milankovitch cycle axial tilt, obliquity. Earth's axial tilt changes over time from about 22.1 degrees to 24.5 degrees. The cycle of tilt change occurs over a period of about 41,000 years. For the first 1.5 million years after the start of the current ice age, this cycle seemed to control the period of glacials and interglacials. After that, orbital eccentricity, 100,000 years, took over. So for the last 1.1 million years, the average time between interglacial peaks has been about 100,000 years. However, the reality is nothing nearly so neat and tidy. The shortest cycle of the last 800,000 years was only 37,000 years long, while the longest was 157,000 years long. Other forcing factors are at work here, but the orbital eccentricity source for climate change, number 5, is strong enough to force Earth's climate back into its own rhythm. What caused the switch from 41,000 years to 100,000 years is still a mystery. Number 2. Milankovitch cycle, longitude of the perihelion, and precession. Perihelion means the closest approach of a planet to the Sun in its orbit around the Sun. The longitude of the perihelion is merely the position of this closest point of approach in relation to a reference plane. This position by itself means nothing with regard to the climate on Earth, but when we combine the direction of axial tilt, it means a great deal. Currently, the Earth's north axis or pole tilts away from the Sun during perihelion passage. This means that the Earth's south polar axis points toward the Sun when our planet is at its closest approach to the Sun. In other words, the southern hemisphere gets far more sunlight during Earth's closest approach to the Sun than does the northern hemisphere. Since the Earth has far more water in the southern hemisphere, the extra warmth received there during the southern summer has to do much more work to raise the temperature there. The overall effect is to keep the planet cooler. Since we currently live in an ice age, we don't want a cooler Earth, because cool climate means less rain, more failed crops, and more starvation. Thankfully, this is not the only forcing factor at work. Number 1. Solar wind. Sunspots seem to be highly correlated with cycles of solar wind activity. Sunspots have a maximum and minimum level on an 11-year cycle. The peaks of these sunspot cycles, spot counts, also seem to obey one or more additional cycles. These involve what are called the grand solar maximum and grand solar minimum. During the Maunder minimum, 1645 to 1715, sunspot activity was at its lowest in recorded sunspot history for an extended 70-year period. This coincided with the coldest depths of the Little Ice Age. We now know that this was a cause and effect coincidence, not accidental. The Svensmark effect explains why climate is so powerfully affected by solar wind. Strong solar wind blows away many of the cosmic rays which attempt to enter the inner solar system. This keeps cloud formation rates at a minimum, forming mostly around dust particles with very few droplets formed by high-speed particle radiation or cosmic rays. When the sun goes quiet, solar wind decreases, allowing more cosmic rays into Earth's atmosphere, triggering a flood of cloud nucleation events that create more clouds, greatly cooling the planet. Discovering this effect was clever science, but is it right? Scientists are still working on this, finding more evidence to settle once and for all whether or not cosmic rays, and thus solar wind, play a major role in climate change. So far, the evidence seems to be overwhelmingly in favor of Svensmark's thesis. Bonus discussion. Notice that CO2 is nowhere to be found on this list. This is not to slight the importance of this vital gas of life. Carbon dioxide plays its part in feeding all of our plants, giving us food and oxygen with which to live. But carbon dioxide has not been proven to drive climate change, or even to be a significant factor. Yes, CO2 is a greenhouse gas. Yes, CO2 has increased markedly in the last half-century, But no, CO2 is still at dangerously low levels. Life on Earth needs much more of this vital gas. All of the pictures portraying carbon dioxide as a dark cloud of soot are an outright lie. CO2 is a colorless, odorless gas without which all life on Earth would die. Please, let's get that one fact straight. Another of the big lies involves the notion that global warming in our ongoing ice age is bad. It isn't. Throughout human history, warming has given civilization prosperity far more often than not, and global cooling has given us famines and societal collapses far more often than not. Any perception of correlation between warming and CO2 increases is an illusion. The correlation is accidental, not cause and effect. We know this because carbon dioxide levels in the paleoclimate record have never driven temperature, but temperature has driven CO2 into and out of the oceans as a dissolved gas. We only need to remember the CO2 fizz in our soft drinks. The warmer the drink, the more rapidly the CO2 escapes. If you get no other point from this video, remember this. Our modern warm period is the most prosperous period in human history, and there are some very nasty people who don't want you to realize this. Greater warmth, more CO2, and human ingenuity are staying ahead of population growth. Don't give in to the pro-death cult. Climate change is 99.99% natural, and our natural warming is helping us to grow more food.